I appreciate everyone listening to this talk right now, and Tony and John organizing this wonderful session. I'm a Takuo Matsubara, who is a PhD student at Newcastle University and the Alan Turing Institute, working with Professor Chris Oates. And today I'm going to talk about the quadrature of Bayesian neural networks. So first of all, there is a theory called Ridgelet Transform, which enable us to construct two-layer neural networks by quadrature methods. And we consider applying probabilistic numerical method for this quadrature-based construction of neural network. And this talk is not about the probabilistic numerical method itself, but about the interesting case where probabilistic numerical methods are applied and useful for building some learning algorithm. So I firstly talk about the problem setting of this research, and secondly, introduce the Ridgelet Transform. And then we will see how Ridgelet Transform enable us to construct neural network by quadrature. And finally, I will show probabilistic numerical method are useful for this scheme, and it fundamentally turn this scheme into Bayesian setting. Okay, so let's move on to the first section. So in this research, we basically consider classical setting of harmonic analysis of neural networks, which have been studied from 1980s. So our neural network model is simple two-layer neural networks, which is expressed as the following summation form. And this neural network consists of n combination of 1 hidden units, which is illustrated in the right-hand side. And each hidden unit has 3 parameters, weight, bias, and quotient. The input bar x is forwarded from bottom to top, and the parameters are used at each step of computation for output. And the entire neural network have n set of these parameters. And the problem we want to think here is function approximation by two-layer neural networks. So let's say this function f is given. Then for given target function f, we want to construct a neural network G, which approximate the target function f with high accuracy. And also we want to make sure that this neural networks G actually converge to the target function f if the number of hidden unit n goes to infinity. So this is a problem setting. And next, I'd like to introduce the Ridgelet Transform. So the Ridgelet Transform is an integral transform developed in the context of harmonic analysis of two-layer neural networks. So roughly speaking, the Ridgelet Transform claims that any function f can be expanded as the following equation here. So I'd like to note that also these functions psi and phi here have to satisfy some special conditions. But basically, there is a certain degree of freedom to pick up the function form of psi and phi here. So for example, this function phi can be Gaussian or hyperbolic tangent or piecewise linear. So there is some certain degree of freedom. And as we can see here, this equation consists of the 2 parts, the first integral here and the second integral here. So in the first part, the original function f is integrated together with some function psi, which have parameter w and b. And this integral transforms, this integral transforms the function f to other function tau, as illustrated at the bottom here. So in the second part, this function tau, this tau means the transformed value in this bracket, is integrated together with some function phi. And again, this second integral also transforms tau back to original function f. So yeah, we can see this illustration at the bottom. And by these 2 integral transform 1 and 2, f goes to tau and tau goes back to f respectively. So I suppose this particular form of the equation is not something common or familiar, but to understand this equation in easier way, we can think this as a relative of Fourier transform. So I think Fourier transform is a more familiar in general. So in the Fourier transform, as long as function f satisfies some sufficient regularity, f can be expanded as following, like here. So the first integral represents the Fourier transform of function f, and the second integral represents inverse Fourier transform. So we can see that the totally same things happens even in Ridgelet transform. So in other words, if we denote the Fourier transform of function f by f hat, then original function f can be recovered by this integral of f hat and the exponential term. So in the totally same way, if we denote this shaded term by tau, the original function f can be recovered by integral of tau and phi. Okay, so this is a quick introduction of the Ridgelet transform. Yes, so it's basically say the function f can be expanded as this equation. Okay, so next I directly explain how this Ridgelet transform enable us to construct neural network through quadrature methods. So as we have seen so far, any function f is expanded as this Ridgelet transform equation. And in order to obtain neural network from this equation, we consider discretization of these two integrals, the first one and the second one. And that discretization of two integrals turns the integrals into summation form, like this. So the first integral is estimated by d point z of x, and the second integral is estimated by n point z of w and b. And now we consider resymbolizing this shaded term as Ci, and which is definitely possible to do because this is just a notational manipulation. And by doing this, now we can see this equation is exactly same as the definition of two-layer neural networks, which I introduced at the beginning of this presentation. So the basic idea is if you discretize this Ridgelet transform of some function f, it automatically gives you two-layer neural networks here. And it is interesting that we can construct neural network which approximate target function f just only by discretizing these two integrals. And this quadrature-based construction also ensures that neural network G converge to original function f in the limit of the summation, because it just comes from the discretization of the integral. I'd like to mention that this formulation have two typical applications. So the first one is the theoretical analysis of neural network. This formulation enables us to analyze some theoretical property of neural network through quadrature between these two equations, and which makes theoretical analysis easy sometimes. So this is the first application. And the second application is that initialization of neural network parameters. So when we train our own neural network, we usually use backpropagation. And to perform backpropagation, we need to initialize all parameters of neural network in advance for sure. And if we use this construction in order to initialize our neural networks, it guarantees that the initial state of neural network is already close to some target function f. So that means we can start our backpropagation with good initial state of neural network, which is preferable for backpropagation. Yes, and I'd like to also mention that this procedure doesn't involve in any matrix inversion. So which means this procedure is basically scalable. Okay, so in this procedure, two integrals, 1 and 2, are discretized by some quadrature methods. So any types of quadrature method can be applied for 1 and 2, such as trapezoidal row or Gaussian quadrature or Monte Carlo method. And this is where probabilistic numerical method comes into the story. So the probabilistic numerical method or the Bayesian quadrature, especially for numerical integration, can be used for any quadrature setting basically. So it is useful to consider applying Bayesian quadrature for this procedure in order to pursue some accuracy and efficiency. And I suppose that Bayesian quadrature itself is already explained by other speakers, and I'm not going to explain the detail in interest of time. But roughly speaking, the aim of Bayesian quadrature is to provide the better estimation of integral value and the probabilistic interpretation. So in Bayesian quadrature, the estimate value of integral is treated as random variable following some distribution. And typically, Gaussian process prior is placed on the integrand f. And because of this prior, the estimated value becomes the random variable following some normal distribution with some mean and variance. So for example, if we apply Bayesian quadrature for integral 1 here, the estimated value ci now becomes a random variable following some normal distribution. And since the I correspond with neural network's parameter, the neural network G also turns into Bayesian neural network rather than deterministic standard neural networks. So what I mean by Bayesian neural network here is neural network whose parameters are random variable. Okay, so yeah, and this combination of Bayesian quadrature and this quadrature-based construction scheme gives us not only better accuracy of neural network, but also quantified uncertainty inherited from Bayesian quadrature, like this picture. Okay, so basically this combination of this scheme and the probabilistic numerical method fundamentally gives us quadrature-based Bayesian neural networks. Okay, so this is a whole procedure to construct Bayesian neural network. Then as the last section of this talk, I'm going to show you some illustrative experiment of this procedure. So I prepare ReLU activation neural networks and construct them based on the Bayesian quadrature, like I already mentioned in the previous slide. The method of Bayesian quadrature I used for this experiment is something called Bayesian Monte Carlo or Bayesian Hermite quadrature. And the task here is to approximate this simple sine function given us 10 data points. Yes, and the full picture at the bottom of this slide shows the output of the neural network, which constructed by Bayesian quadrature. So, for example, in the right-hand side picture, we can see that the output of the neural network captures this sine curve well, with some quantified uncertainty between each points. And we can also see that the output of neural network get better and better when the number of hidden unique n goes to larger and larger. Okay, so we also compared the standard quadrature-based neural network and Bayesian quadrature-based neural network. So, I mean, this first two pictures shows that the output of neural network, which constructed by classical quadrature method, such as Gaussian-Legendre quadrature or something. And this third picture shows output of Bayesian neural network, which is constructed by the Bayesian quadrature. This is the same neural network as the previous slide. So as we can see here, since we only have the 10 data points, the neural network constructed by classical quadrature fail to capture the sine curve behind the data. So the first picture shows some it's not complex enough to represent the sine curve. And the second picture shows that this is basically just overfitting to data. And on the other hand, the Bayesian quadrature gives us a better output of neural network. Okay, so this is a sort of illustrated toy experiment. So to conclude in this talk, I quickly reviewed the Ridgelet transform and how it enables us to construct neural network by quadrature method. Then I discussed the probabilistic numerical method, with this scheme fundamentally gives us a quadrature-based Bayesian neural network. I haven't talked the detail. This talk is a quite introduction, but this formulation based on Bayesian quadrature and the Ridgelet transform is useful to show more general theoretical property of Bayesian neural network, such as convergence rate or certain consistency. So the set of our new and the more general result will be online soon as well. So yes, so this is the end of presentation. Thank you so much for listening.
Thank you, Takuo. One of the things I was wondering, maybe you mentioned it and I missed it, but so in what sense this Ridgelet transform is an approximation to the original function?
Okay, yes, that's thanks for asking. That's a great question.
Or what I kind of mean is that is there a selection of these functions and the measure such that this is not an approximation but an equation?
Yes, actually, okay. So the meaning of approximation is my answer involves in this measure here. So basically, we can show that if we set Lebesgue measure for this lambda, this equation converges to original function f. So this is the meaning of the And if we place some other probability measure, for example, some Gaussian measure or something, then this equation becomes the approximation of original function f. So the meaning of approximation is so that if this lambda, so we want to place finite measure for lambda here, and this finite measure lambda is close to the Lebesgue measure. This equation also close to the original function f. This is the meaning of the approximation.
Oh, I see. So okay, if lambda were a Lebesgue measure, then this would be an equality. Is that what you're saying?
Yes, yeah. If lambda is a Lebesgue measure, yeah, this becomes an equality, yeah.
But if lambda is a Lebesgue measure, then you cannot actually compute things. Is that the point?
Yes, exactly. For the computation, we want to place some finite measure for lambda. Yes.
Okay, thank you.